I'd like to share a story with you, the story of two people. So this is Petra. Petra is a 60-year-old German architect. And since the start of her menopause, she noticed that her hair was falling quite a bit and her hair volume has decreased. And so she got a bit worried and she went to see her doctor. And together they decided to start a treatment with minoxidil, a medicine used to treat hair loss. This is Jason. Jason is a 47-year-old accountant from Australia. He's been bald since his mid-30s, but for some reason of his own, he has decided to also start minoxidil to stimulate hair growth. So on first look, there is not much in common between Petra and Jason, except maybe their beautiful smiles. But unfortunately, few weeks after the start of their treatment, they start to develop side effects. They both feel slow and dizzy and have this lingering pain in their head. So they both went to the doctors and they talked about their symptoms, what happened. And the doctor made an assessment, a general assessment of their patient. They looked notably the blood pressure and noticed that it was quite high. The doctor agreed that the timing was such that maybe this is drug-related, and they filed in case reports where they described that their patient had taken minoxidil to treat hair loss and described what happened afterwards and the kind of symptoms the patient experienced. So these reports were then sent to the national pharmacovigilance centers of the respective countries, so Germany for Petra and Australia for Jason. And at those national pharmacovigilance centers, the case reports were reviewed by pharmacovigilance specialists who looked at the descriptions of what happened to the patients, and to ensure good harmonization and also good future analysis, they had to encode what was described in free text into one single regulated terminology called MEDRA. So Petra's case report was encoded as such: sluggishness, dizziness, headache, and hypertension. Whereas Jason's case report, the specialist chose fatigue, dizziness, headache, and blood pressure increased. So let's not forget that under the hood, it's really the same bodily response that happened to both Petra and Jason, but in the end, it was encoded differently. So case reports such as Jason and Petra's, they can be generated in many places in the world, and they're being collected by those pharmacovigilance centers, and then they're being sent to VGBase, the WHO database of individual case safety reports. And we at UMC, we are collecting all these reports and we're maintaining VGBase. Today, VGBase contains more than 20 million reports from more than 130 countries. So, finding previously unknown safety concerns with medicines or finding new aspects of previously known side effects is what we're trying to do at the Uppsala Monitoring Center. And we, data scientists at the research section, we're trying to develop new and better ways to bring forth those potential safety concerns. And this brings me to the core of this presentation. I want to share with you the result of a pilot project that I did that I think has the potential to bring really new advances in pharmacovigilance. But let's start at the beginning. At the beginning of my employment at UMC, I am just a data scientist that knows nothing about pharmacovigilance, but nonetheless, I want to build cool models that will do this safety monitoring for all the benefits of the patients. But I can see that I have one big hurdle to deal with the case reports. It's the way the concepts like drugs and side effects are represented. So you remember in the case of the side effects on Petra and Jason's report, they were all encoded into one regulatory terminology, which is MEDRA. And MEDRA is rather large. We have like 20,000 different terms in VGBase that we can see, and they range really from like myocardial infarction all the way to acute psychosis. So navigating this really long list of terms can be actually quite challenging and requires a lot of training and a lot of expertise from the pharmacovigilance specialists. And of course, it also brings a certain amount of subjectivity. So I really wanted to build models that will be a bit agnostic of this subjectivity and can take into account a sense of similarity between terms. Because if you remember from the reports of Petra and Jason, we had two sets of terms that actually differed in the way the specialists encoded them. We had sluggishness and fatigue. That turns out to be recognized by MEDRA as two very similar terms because they share a very early common branch in this tree. But, hypertension and blood pressure increased, unfortunately, turns out to be sitting at the complete opposite of the tree, and they do not share a common branch at all. Hypertension is under vascular disorders, while blood pressure increase is seen under investigations, which is where you find all the terms related to medical test results. So there were really three aspects that I felt were really not ideal with the way side effects were represented in my data. The first thing was that they were very discrete, and if I would want to use representations of them in machine learning model, I would have to use a very long and very sparse vector. There is only a very rough sense of similarity that is captured within this MEDRA hierarchy. And the representations have been manually decided, and it can have some very unfortunate consequences, like in the case of hypertension and blood pressure increased. What I wanted to have instead would be representations that are continuous and would be low-dimensional when compared to the entire vocabulary size. I wanted to capture a much more nuanced sense of similarity and hopefully build all this in a data-driven way. This is what I wanted to build. Isn't this beautiful? I wanted to build a space of meaning, a space where similar terms like sluggishness and fatigue would end up very close, and so would hypertension and blood pressure increased in another region of the space. I wanted really this space to carry that information about similarity. Maybe this problem sounds familiar to some of you, because finding dense representations of concepts instead of very sparse ones is actually not a new problem, and it has been addressed in another field, in natural language processing. So in natural language processing, the task becomes about building a space of meaning for all words of a certain language, let's say English. And to address this problem, distributional semantic methods have been proposed. So most such methods are actually data-driven entirely, using large text corpora, and so they are unsupervised, which is a very desirable behavior. And they're often based on co-occurrence patterns within context windows. They're really using the principle that I think is best summarized in this quote: "You shall know a word by the company it keeps." And in other words, you, and more interestingly, the machine, can start to understand the meaning of a word by just looking at what kind of context it appears in. So the most popular distributional semantic methods are word2vec, developed at Google, and GloVe, developed at Stanford. So I thought, okay, great. This looks like it could help me solve my problem. Let's try to use word2vec on VG-based reports. But first, I want to tell you a little bit on how word2vec works. So it takes an entire text corpora. In this case, let's imagine it's just a sentence. Let us not fall asleep during this presentation. I hope you agree. And in the CBAO implementation of the word2vec algorithm, the task is about predicting the center word, in this case, asleep, using the context words, here for a context window of 2. And to do so, you model the probability of observing the center word as a function of the representations of the word and the representations of the context window words. And basically what you're trying to do is to maximize the log likelihood of your words over the entire corpus, and to do so you apply gradient descent like optimization to get to those representations that you desire. So I thought, well, let's use this principle on VG-based data, on all the reports that we have. Because, after all, just like a sentence is a collection of words, a report is a collection of terms. But there is one important difference here. A sentence is a sequence. Order matters in the sentence. While in reports, there is no natural way to actually consider an order between the different terms. So I was trying to adapt this method to set-like inputs instead of sequence-like input. But I actually failed, and instead I thought, well, let's cheat. And I cheated instead, and sometimes it can be a good idea. I just randomly assumed an order and make my reports sentence-like. I was wondering if 20 million reports would be enough to actually cancel out that effect of assuming a random order. And lo and behold, it did work. It turns out that at the end of the application of word2vec, I ended up with a space that had a lot of meaning in it. Here are some examples. So, top 10 closest neighbors in the space when we look at myocardial infarction and suicide ideation. And let me tell you that the algorithm does not know anything about the actual word inside those expressions. It is really just based on the co-reporting patterns within VG-base that it could magically learn that all these terms are actually a lot of relatedness. But of course, eyeballing a little bit of terms here and there, it's not a very satisfying evaluation measure. So I wanted to address this evaluation in a more systematic manner. Then I realized, well, I can use Medra. Because Medra being a hierarchy, I can look at things that are supposed to be closed according to Medra and see if indeed they are in the space. So here's the result of this evaluation, and I plot here the cosine similarity distribution depending on the kind of pairs I'm sampling. So if I'm sampling pairs of terms for which they share a very early common branch in the hierarchy, meaning Medra believes that these two terms are very similar, we obtain the light gray curve, and as we see, the light gray curve is more shifted towards high cosine similarity. And as we go down in the tree and relax those constraints on sharing common branch, similarity drops all the way to when we actually just sample terms at random and look at their similarity. I also got interested in evaluation of the quality of the representations. I thought something to look at would be how the algorithm deals with data quantity. So this is what you kind of expect. If the algorithm has very little information to work with, just very few contexts to look at, the representation should basically reproduce random noise, while very frequent terms should obtain good quality representations. But of course, I could not build that graph directly because intrinsically, one single vector is not good or bad. It's how they relate with one another that is important. So I used Medra again. So I looked at all pairs of concepts that were deemed to be very similar according to Medra. And then I sampled only those that were having one of the terms seen only once. So imagine 20 million reports, 40,000 unique terms, and among those you have some terms that are seen only once. So for those pairs, I was expecting that the similarity distribution would be basically random. So if I compute the cosine similarity between those bad represented terms with anything else, I should see something that is basically random. But it turns out I didn't see that. So it seems like Word2Vec is powerful enough to start to make sense of a term with as little as one observation, because we clearly see that this light gray curve is shifted from what you would expect under taking random pairs. And we also see that effect that the more data you have, the better the quality of the representations, because we expect a high cosine similarity between those pairs. And indeed, we start to see that shift. I made many more evaluation of all this space. It will be made available in this publication, but for now, they are editing the proceedings. So, yes, so I could make this space. It seems to work somehow, and I was very happy. But what does it mean for pharmacovigilance? How can we use that? Well, so far, since we're quite early in the stage, I can only speculate. But I want really to stress that it's a very clear paradigm shift for the field. We are going from discrete representations with a very rough sense of similarity and are manually decided to something that is continuous with a very nuanced sense of similarity and is completely data-driven. So some potential low-hanging fruit that I can see, we have everything related to customizable term expansion. And by that I mean you might have terms of interest and you might want to explore their neighborhoods, what's around it. And I think this can help to support the work of pharmacovigilance specialists. Like in the case of Jason's specialist, he might have seen then in the vicinity of fatigue that there was this term, sluggishness, which indeed is a better description of feeling slow than fatigue is. I think it can also help with the safety detection at the level of neighborhoods, so regions, instead of single term, for single medicine versus single side effects. I think really harvesting this power of the neighborhood can make our statistical methods much more robust. And let's not forget that now we have new kinds of input that we can use into our machine learning models. And those new inputs are much more reflective of actual meaning. Yes, so it's still very early, and I think starting from now, imagination is the limit. And if we consider how much word2vec and glove and this kind of distributional semantic methods have completely revolutionized the field of NLP. I'm very excited about the future of pharmacovigilance methods. So this is the end of my story, but it could be the beginning of yours. If you're interested in applying your creativity and your data science skill to improve the world of patients, you can send us an email or drop me a line because we are actually recruiting. So now I welcome any kind of questions, any kind of ideas, and I thank you very much for listening.